Greetings to you. Welcome to Physics with Ben. In today's video, we want to construct an electromagnet, otherwise known as a solenoid. This is a branch of physics called magnetic field. Magnetic field is a region or a space around which the influence of magnetic force of attraction or repulsion can be felt or experienced by an object placed in it. Magnetic field is a vector quantity having both magnitude and also a specified direction. So a solenoid is simply a temporal magnet that behaves like the bar magnet. This is the bar magnet, and here is the compass needle. So if the compass needle, the red side of the compass needle, we always point to the north side, to the south pole of the magnet, while the other side, this side will always point, this other side will always point to the north pole of a magnet. Right now, there's no magnet here currently, but you can see that this guy is pointing in this direction. We are told in physics that the Earth has an imaginary bar magnet inside its core. This is based on the behavior of the compass needle when it is placed. The compass needle, the red side is pointing in this direction right now. I told you the red side always stands for the north pole. So, always stand for the north pole. Now, it means that this side, that the red side is pointing, is the Earth's geographic south pole, while the other side facing me is the Earth's geographic north pole. Red will always attract north, and this will also attract the black side will always attract north. Black north, red south. So Earth's geographic south pole, Earth's geographic north pole. The compass needle is used in magnetic field to detect the presence of magnetic field. That's number one. Number two, to detect and show the direction of the magnetic field strength. I told you magnetic field is a vector quantity. It is a vector quantity, and if I place two bar magnets here, you observe something quickly. If I place two bar magnets here, you observe something. Just observe this little experiment. The direction of magnetic field. You will discover that, just discover something quickly. You can see that these guys, they are pointing to the south. It means that the direction of magnetic field is from north to south pole, just like the direction of electric field is from positive to negative terminal. So what I just did here right now is to trace the magnetic field lines. They are imaginary lines that are drawn to map out the direction of the magnetic field strength. So right now we are going to go straight to why we are here. In constructing the electromagnet, you may choose to use the copper wire, which is this one, or you will use this particular one. They are very affordable in the markets. So we need the cells. You may I'm going to use two of this rod and this one. So we need cells 1, 2, 3, 4, 5, 6, and these are the connection wire with the crocodile clip. We are going to see how we're going to use all this. These are called battery rackets. So these are iron filings to test if the electromagnet will actually attract the iron filings. So let's begin. We are going to pick this rod and we are going to wound this around this. Now before I do that, I want to remind us of something quickly. For an electromagnet, for us to increase the strength, the magnetic field strength of an electromagnet, it is increased based on the number of turns of the wire. So let me just start doing that right now. So I'll be turning this around here. Yeah, something like this. So this is what I was saying. So the strength of this magnet is dependent upon the number of turns. This is what I mean. So it is dependent upon the number of turns. You see this? Yes. So we are going to connect this to the battery later. So we're going to use the two of them. So right now we are going to wound this. Well, I'm doing this alternatively. This is a copper wire. You have seen it in the market before. You can go and get it and then also run this experiment at home. So we're going to wound this copper wire the same way we did this other one. So we're going to wound it round like this. Then you take it clockwise. You go round and then wound it round. So you keep turning it. So the number of turns, more number of turns will give you more magnetic field strength. More number of turns will give you more magnetic field strength. You turn it this way, turn it this way. So we are done with this. So we'll cut it. It's too long. We'll cut it down here and then peel out the copper, the coating on the wire so that we can have good electrical contact. Peel it like this. So we are going to use the two of them for this experiment. So we have this and then we have this. So let's try the two of them. So as I was saying, the compass needle has so many uses in magnetic field. Number one, it is used to dictate you may have a magnet without polarity, but with the help of the compass needle, you are able to know if it is north or south you are dealing with. That is one use. Because if the north is pointing toward the magnet, if this red side is pointing toward the magnet, it means that magnet, the side this guy is pointing to, is the north, is the south pole. If this side is pointing toward a particular magnet without leveling, you can know that this side this guy is pointing is the north pole of the magnet. Just like a test charge will always tell us the type of the point charge in an electric field. So does the compass needle behave. It is a very, very important tool in the magnetic field. With the help of this compass needle, the application of this compass needle, the mariners, the pilots, they use this to navigate their way in space and in the sea. Very, very important tool in physics. So the next thing we are going to do right now is we are going to connect our battery rackets together. We're going to connect this in series. We are going to connect this in series. So these are our battery rackets. We'll connect them like this. So we are done fixing or fusing our battery rackets together. So this is 1, 2, 3, 4, 5, 6. 6 cells. The next thing is to connect the... Now before we do that, let's test something quickly. Mind you, watch something. You see this? You see this? You see this? You see this? Good. Now, if I bring this guy, you won't see that because there's no magnets. Even though you may see that there's a little deflection here, it is correct because every material that is metallic in nature has little magnetic property in it. However, the magnetic dipoles are not aligned. But when we pass through a direct current, we are going to align the magnetic dipoles, and then we are going to give the rod polarities, either north or south. And also the polarity of this solenoid or this electromagnet is dependent upon the polarity of the cell. We'll see that as we connect them together. So, I was saying something very, very important. There are two ways to increase the magnetic field strength of these electromagnets. By increasing the number of turns, that is number one, and by increasing the EMF from this direction and from this end. So now let's begin. We're going to connect. This is negative, negative. So this is one cell, two cells, that's a battery. Two cells give a battery. This is 3 cells, 4 cells, 5, and then the last one 6. So let's begin. Observe something. Good. I'm going to draw a circuit diagram for this arrangement. Right now, the compass needle, they are pointing toward the Earth's geographic south pole. But the moment I pass in a direct current, you're going to see something. So I'm going to connect one side of this crocodile clip here, as you can see, and then I'll connect another one to this end. Let's start with one cell. So I'm going to bring this close here. I'm going to bring this close here so that you observe what will happen. So one end will be connected here. Please pay maximum attention. Now we are dealing with one cell. Observe something. Good. It worked. I will remove it. You observe something again. What do you see? Lovely. I will connect it back again. You will see. So right now what we are having here is that the red side, this red side of the compass needle is pointing here. It means that this electromagnet, the end that is connected to the negative side of the cell is the south pole. Right now, this is the south pole. So label it the south pole of the electromagnet. Here is the north pole of the electromagnet. So let us increase the magnetic field strength of this electromagnet by increasing the EMF. So put it by 2. See that the deflection is becoming stronger. We'll put it at 3. We increase it. You can see that the strength of the magnet is increasing. We'll put it at 4. It's increasing. Let's put it at 6. That is 1.5 times 6. Do you see that? Let me lift it up so that I can see it proper. You see that? Good. Now, I want to take this guy to this side and this guy to this side. Observe something quickly. and see what will happen. This side is still our south pole. This side is still our north pole. This is the north pole of the electromagnet, and this is the south pole of the compass needle, pointing toward the north pole of the electromagnet. Good. Now, let us try this guy and see if this guy will also work for this. We'll remove this and bring in the other guy. Physics is very sweet and very simple. The theories in physics, they are not abstract. So watch. Good. It also works. But it seems that this one is more effective. So you can choose the one you want to work with. It seems the other one is more effective, but you can see the behavior of the compass needle. So from this experiment, it's believed that this one, this particular one is more effective. So let's go with this one. But yeah, this one gave us also the answer. Now the next thing I want us to do quickly before I stop this video is for us to alternate this pole. If I alternate this pole right now, I'm going to take this side of the connection to this side. Just watch what I'm doing. I am alternating. So right now, our positive is this side and our negative is this side. So I'm going to connect it back to the solenoid. Observe something. It will give you a different reading right now. So the second connection is telling us that you can see the black side of the compass needle is pointing here, meaning this time this is our north pole, and this time the red side is pointing here. This time this is our south pole. So confirming that the polarities of a solenoid is dependent on the polarity of the cell involved. The next thing I want us to do quickly before I end up this video is to see if this electromagnet will attract these ion filings. An electromagnet is an example of a temporal magnet. We are going to raise this up and dip it in here and see if it will attract these ion filings. Yes, you can see that there are ion filings. There are ion filings on top of this ion. Now, it's a temporal magnet. Watch what I'm going to do. I'm going to disconnect one of these here, and you observe that all the ion filings will drop on the paper. Let's try. 1, 2, go. Good. You see that? I'll do it for the second time again. This time I'll also alternate the battery again and do it as I did the other time. So I'm going to dip this here and observe what will happen. Good. What do you observe? Good. You can see a bunch of ion filings on the solenoid. I'm going to take this, disconnect this here. The moment I remove the EMF, everything there will fall down. Okay, let's go. 1, 2, go. That's it. So the circuit diagram for what I have done here is simply something like this. You can, what I did here is called the I shape, electromagnets. It's something that looks like this. This is the rod, and this, the solenoid connected to something like this. So as I say, connected to the plus, to the negative side, to the negative, when it is connected the way it is right now, it is plus to negative. Let me turn it quickly. This is plus to negative. This is exactly what you have here right now. Let me do it proper. So this is what you have here right now. This is it. So good. Sorry. Good. This is the circuit diagram for this arrangement. So the current will flow in this direction and back in here. So what you have here right now, this is right now, this is the north pole. This is the north pole, and this is the south pole, based on what we have here right now. The north pole, and that is the south pole. This is the north pole, and this is good. Yeah. This is the north pole of the electromagnet. So to this we have come to the end of this experiment and this video. Don't forget, this is the circuit diagram. What I have just explained here, this is the arrangement. Don't forget to subscribe to this channel, to share this video that need it. Thank you. God bless you. Bye bye.